Welcome everybody to the Droid Connectivity webinar. Let's not wait anymore, let's kick off. Thanks, Martin.
Okay, no problem. Thanks so much for your patience. I'm assuming there are at least 2 or 3 of you still out there. Really appreciate you hanging on. Difficult times, of course, and it's great that we can get together and do some knowledge sharing. I'll introduce myself. My name is Martin Woolley, and I work for the Bluetooth Special Interest Group. Just in case you've never heard of us, we're a standards organisation, and essentially we're the company behind Bluetooth technology. So we're not a manufacturer, we don't make anything, we don't make products or software. We're only responsible really for the technical specifications that define how Bluetooth works and how it should be used in different types of product. That's who we are and what we do. Now, I've had the opportunity to speak at Droidcon Italy a few times over the last few years, and I've focused on specific topics on those previous occasions. I want to take a different approach today and I've picked out a few topics that in a sense are related only in that they're probably not as widely understood or known by developer communities. And to fully appreciate them probably requires more knowledge than is the case for a typical application. So we're going to go in deeper than usual. I'm going to kick off with some basics, but I'm not intending to spend very long on them. If you find that you have gaps in your knowledge and things are not always sticking as we go through the more advanced stuff, don't worry, because I'll point you at some resources at the end that will help you plug the gaps after we finish this interesting conversation that's already got me sweating. Let's see how this goes. So let's start with some basics. So as you probably already know, there are essentially 2 types of Bluetooth. Bluetooth is a radio communications technology. The original Bluetooth is called Bluetooth BR EDR, that's basic rate enhanced data rate, and it's been around for 20 years. It's still used a lot for things like audio, and if you've ever used the serial port profile, you've been using Bluetooth BR EDR. Now, Bluetooth BR EDR can only support point-to-point connections between 2 devices. It's essentially a cable replacement technology. It's exactly like working with serial data transmission across an RS-232 cable, except there is no cable. Bluetooth Low Energy is newer, but it's over 10 years old now. Originally designed to be very power efficient, hence the low energy part of the name, but it's also much more versatile. You can form point-to-point connections just as you can with BR EDR, but you can also broadcast information, and broadcasting means that one transmitter can communicate with an unlimited number of devices that are receiving. They just have to be in range, but there is no limit to the number of devices that can receive a broadcast from a suitable device, which is pretty powerful. And then we have Bluetooth Mesh, which is a whole Bluetooth technology in its own right. And with Bluetooth Mesh, you can form potentially quite large networks, tens of thousands of smart devices. It's used in smart buildings for monitoring, control, and automation of building services and devices and so on. And it actually uses Bluetooth Low Energy under the networking layers for its wireless communication. Now, if you ever developed a Bluetooth application before for Android or any other smartphone, you'll know that typically the way things work, the kind of standard flow of your application, involves initially a discovery phase where you need to discover devices that are in the environment and try and pick out those ones that seem relevant to your applications. That's called device discovery. And the way that works is Bluetooth peripheral devices are doing something called advertising, which is a way of broadcasting data designed specifically to attract attention to that device, convey some information about what type of device it is and what kind of capabilities it has, so that you can make sensible decisions about which ones to offer to the user, maybe in a list, for them to select from. And you have a number of classes available in your Android APIs. So Bluetooth LE Scanner will kick off the whole scanning process. That's the term we use for looking for advertising packets. And you can filter out packets that are clearly irrelevant, and there are various other settings you can use. And eventually you get a collection of Bluetooth device objects, and from that you'll let the user make that final choice. Once a device has been selected, you'll connect to it. Other devices will continue to advertise. You're not interested in those. The one that you've connected to will almost certainly stop advertising because it's now in the connected state. Now, once you're in a connection, you're going to be working with a table of data on the remote device that's called the attribute table. You don't often see this written down in API specs, but that's what it's called. And sitting inside the attribute table are a series of attributes, kind of rows in a table, and they're all of one of three types. There are services, characteristics, and descriptors, and collectively they form a kind of hierarchical structure which has been flattened to fit in a table. Now, services act as a kind of grouping mechanism. They contain characteristics, and characteristics are really just data items that have a specific type. They have a value, and they support various operations that the remote connected device can initiate, things like reading that value, writing to it, and something called notifications, which is a facility which, when switched on, will result in characteristic values being delivered to your application at the other end of the connection, either periodically on a timer or every time the characteristic value changes, something like that. Now, sitting below characteristics at the third layer are descriptors, which are completely optional. So some characteristics have them and many do not. They allow us to do things like switch on or off those notifications that I just mentioned, or they provide metadata that further describes the characteristic they're associated with. And as you can see, you've got a bunch of classes in the Android APIs that represent these attribute types, and there's something called Bluetooth GATT, which gives you control over the various operations. GATT itself is a technical term. Should we have a look at my next slide? It comes from the Bluetooth stack. So the Bluetooth Low Energy stack on your Android device looks like this. It has two major component parts. The top blue box is called the host. It contains a bunch of layers of the protocol stack. And sitting underneath that, we have something called the controller, which is the grey box. And it also contains a couple of layers of the stack. And that all sits on top of the radio, which is a hardware component of your smartphone. Sitting in between the host and controller, there's a defined interface called the host controller interface, or HCI, and that defines some commands that can come down from the host to the controller, and events which go in the opposite direction and communicates results and information back up to the host. Now, as an application developer, most of your interest lies in the top layers of the stack. The APIs that you're going to be using will be driving GAP and GATT procedures and using the attribute protocol to kind of have a conversation between the two devices. Now, GAP is concerned with device discovery and forming connections. GATT, the generic attribute profile, we saw that term in the API names, is concerned with procedures that involve working with that attribute table on the remote device. The way those procedures get conveyed and executed involves a conversation that takes the form of attribute protocol PDUs, protocol data units, being exchanged by the two devices. So when you call an Android API, what you're really doing is driving a GATT procedure, which will be executed in terms of one or more exchanges of attribute protocol PDUs. That's what's going on behind the scenes. Now, what I want to do now is take you through a number of issues and Bluetooth capabilities that Android has these days, particularly newer devices. I'm going to start here with the topic of data rates. And this relates to Bluetooth Low Energy when used in a point-to-point connection with an Android device. Now, data rate is a surprisingly complicated topic. Now, most of the time, we don't really care about it too much. Most of the time, Bluetooth Low Energy devices are exchanging quite small amounts of data. Maybe a sensor will deliver a reading, a value, which is 1 or 2 bytes in length. So data rate is generally not on our minds at all. But sometimes there are situations such as, for example, where your application or a remote device will accumulate data in a disconnected state over a period of time. And then when you connect, you have a relatively large amount of data you want to transfer from A to B as quickly as you can. And we want to do it quickly, typically because we're concerned about user experience, probably for no other reason than that. So there are ways of maximizing the data rates as measured at the application layer between two devices, but there are lots of factors, and it's a bit more involved than you might think, and this is where more advanced, kind of deeper knowledge of the subject becomes very useful. It will certainly help you make sense of the APIs. Oh, could somebody mute their phones, please, or their headset? Yeah, I can hear somebody. It'd be really cool if everyone could mute. Thank you very much. So let's start here. I'm going to explain to you the various factors that influence data rates as measured at the application layer. The first is to understand this. Bluetooth is a radio technology, and radio is analog. It's not digital. We can use it to convey digital data, but it's analog. And the way that we represent digital data, as in ones and zeros, binary data, in radio signals, is through something called a modulation scheme. Bluetooth uses something called frequency shift keying, which means that if you consider a given central frequency to represent a 1, we shift that frequency up a little bit. That's called the frequency deviation. It's 185 kilohertz, in fact. So we increase the frequency by 185 kilohertz to represent a 1 and transmit that signal for a period of time. To represent a 0, we take the same central frequency and we drop it down by 185 kilohertz to represent 0. And these bursts of signal at one of these two frequencies is called a symbol. So a symbol is the kind of analog equivalent of a bit in the digital world. And of course, there is a rate at which we can transmit symbols. Now, in the world of Bluetooth, the modulation scheme we're using is called a binary modulation scheme because every analog symbol corresponds to one digital bit. And therefore, the symbol rate, which is 1,000 megasymbols per second by default in Bluetooth Low Energy, corresponds to 1,000 megabits per second. So this is kind of our start point for understanding what the possibilities are. We've got 1,000 bits per second to work with because we've got 1,000 symbols per second being generated at the physical layer right at the very bottom of the Bluetooth stack. So bear that in mind. I'm prepared to be disappointed because with our 1,000 bits per second at the physical layer, you're not going to get that or anything like it at the application layer. And here's why. Much of the data, much of those bits that get transmitted in a packet aren't your data. They're protocol-related bits and bytes, and they consume some of your bandwidth. So on screen, I have a link layer packet. This is essentially what goes over the air. And only 2 bytes, 16 bits of the total of 168 bits are my application data. The hex E803, that's my data. That's what I'm trying to write to a remote characteristic. But there's all this other stuff which is there for the protocol to work. It's a kind of fixed header, if you like. So consequently, my application data is actually a small proportion of the data being transmitted in a packet. And therefore, from the viewpoint of my application, I'm actually only going to get 95 kbits per second in this specific example. Now, those of you who are thinking ahead will probably realize that if I was transmitting more application data in my packet, and if those headers are fixed, which they more or less are, then I'll have a greater proportion of the bandwidth being used by my application, and the application layer data rate will increase. So one of our techniques is to send more in each packet, therefore we're getting more of the bandwidth for application data purposes as a proportion of the whole. 1 point, in italics down there, all of these calculations, they assume continuous transmission, that 95 kbits per second of 16 bits off of 168 over a 1 megasymbol per second physical layer. That assumes continuous transmission, which is not how it works, as you shall see. Now, there are a number of variables, and symbol rate is one of them. Packet size and the proportion of application data is another one. I'm going to take you through some others now. Most of them you have some control over. The MTU stands for maximum transmission unit. And every layer of the protocol stack forms part of the packet which is eventually transmitted over the air, and the part that it contributes is called a service data unit, or SDU, and there's a maximum size that applies to SDUs at each layer of the stack. Now, your concern is attribute protocol. That's where you're working with your APIs, and the attribute protocol has an MTU. Now, our concern is to make the MTU larger because we like to pack more application data in per packet so that we get a higher data rate overall. The default is 23 bytes or octets. It means the same thing. But if you look at the packet breakdown at the top there, you'll see that the attribute protocol part of the PDU in green, 3 of those bytes are actually consumed by protocol data. There's an opcode and a handle value, which is an index into the attribute table on the remote device. So you're actually left with MTU minus 3, or by default, only 20 octets per operation. Fortunately, devices will support larger MTUs typically. Only the very old devices will support no more than 23 octets usually. And you can ask the remote device to increase the MTU size. And in fact, there's an exchange of information via the attribute protocol and something called exchange MTU. And the two devices will figure out what the maximum MTU is that they can both support. So you can expand it quite considerably, potentially. I'll show you the APIs for that in a moment. Sitting underneath the attribute protocol is a layer called L2 cap. Actually stands for the Logical Link Control and Adaptation Protocol, but that's a big mouthful, so we just call it L2 cap. Now, the L2 cap is the lowest layer of the host, and the next thing we have to do is communicate with the controller, which is contains at the top of it the link layer. Now, the link layer has its own MTU. It's possible that the controller is from a different manufacturer to the host, so there could be all sorts of variations. So one of the things that L2 cap does is, if necessary, it will chop attribute protocol PDUs into a series of smaller link layer packets. That's a process called segmentation, and it will do that in accordance with the MTU supported by the link layer. Now, the issue here, of course, is that more packets means more fixed overhead from protocol data, and that reduces our bandwidth. So once again, what we'd really like is to see fewer link layer packets so we get a higher proportion of our bandwidth available for our application data. Now, luckily, Bluetooth 4.2, I'll talk to you about kind of versions later on, introduced something called the LE Data Packet Length Extension, which is a capability that allows link layer packets to be significantly larger if both devices support it. And if they do both support it, it'll be used automatically or automatically, if you prefer, without you needing to do anything, but that will significantly reduce the number of link layer packets and therefore the overhead of protocol bits and bytes, and therefore improve your throughput at the application layer. Now, this is an interesting and potentially complicated topic. Connections, what does it mean? If we plug in a cable between two devices, we have a pretty clear idea of what a connection kind of means. There's a physical thing involved there. But with wireless communications, a connection is something a bit more esoteric. When two Bluetooth devices form a connection, essentially they have a conversation and a negotiation regarding various parameters that will then govern the way that they communicate with each other. And many of those parameters are concerned with timing. You have one radio. The radio can do one thing at a time. It can transmit, or it can receive, or it can be idle. And only one application can be using it at any specific point in time. So there's a need to do some time sharing here so that multiple connections can be serviced at the same time. And some radios, by the way, physical radios in the hardware, support multiple protocol stacks. So maybe it's not just Bluetooth using the radio on your smartphone. So the way Bluetooth approaches this kind of time scheduling and sharing issue is through two concepts, the connection event and the connection interval. A connection event happens every so often, and that time period is called the connection interval. It's one of the things that's negotiated when we connect. When a connection event happens, and it relates to a specific connection, that's the opportunity for the first device to transmit. One device will take on the role we call the master, and it's kind of in charge and it drives communication. The other device is the slave. Every time a connection event occurs, every connection interval, milliseconds or seconds, the master can transmit a packet. It will then sit and wait for 150 microseconds. That's a fixed interval called the interframe space. The slave will then reply. In fact, the slave doesn't have to reply to every packet, but for the moment, let's assume that it does. And they take turns in this fashion, master transmitting and then waiting, slave transmitting and the master receiving. Now, the connection interval is of a certain length, but it's not the case that the entire duration of the connection interval will be used by the master and slave for the purposes of exchanging packets. The specification actually only stipulates that one packet should be sent, and implementations are free to do whatever they want after that. Restrict themselves to a single packet in the connection interval or try and pack more in. And this is a scheduling question, and it's an implementation issue because the scheduling requirement will vary from device type to device type and depending on how many connections are being serviced and things like this. So all we can say about connection events and connection intervals is that the more often a connection event occurs, the shorter the connection interval, then the more often the master device has the opportunity to send some data. Okay, so clearly that's likely to help with our throughput, but we're not necessarily going to be using the whole of the connection interval. And connection intervals can range from between 7.5 milliseconds at one end of the spectrum and 4 seconds, which is very infrequent at the other. Android gives you a number of, well, gives you an API called request connection priority, and it doesn't let you request a specific connection interval measured in milliseconds. It gives you 3 figurative constants, balanced, high, and low power. So high means very frequent connection events, so you can probably get your best throughput using that class of connection priority. Low power means very infrequent because you're more concerned with conserving battery power, and balanced is somewhere in between. You've kind of seen this slide or something very similar to it already. If we drop right back down to the physical layer, the 1000 megasymbols per second that I described at the beginning actually is only one of several possible options depending on the version of Bluetooth the two devices are using. Because Bluetooth 5 from about 3 years ago introduced 2 other ways in which the physical layer can work. And those 3 schemes, we call them PHYs, P-H-Y, that's the kind of abbreviation, if you like, for physical layer operation modes. The original 1000 megasymbol per second PHY we now call LE1M, but there's a newer one from Bluetooth 5 called LE2M, which has double the symbol rate, it's 2000 megasymbols per second. Now, obviously, you'd expect that data rates would be faster if you use a symbol rate which is twice the size. And it probably will be, but it certainly won't be twice as fast because there are lots of other variables at play here, as I hope you're beginning to understand. If our connection interval stays the same and the scheduling in the particular implementation of Bluetooth on your device, and remember this is outside of our specifications, doesn't take advantage of the fact that we have a higher symbol rate and it still schedules the same number of packets every connection event, then you probably won't see much of an improvement in overall data rate. The benefit instead will be something we call spectral efficiency, because you're not using radio spectrum for as long. You're using it for half the time, so that's a great scalability benefit for situations where there are large numbers of devices communicating in the same area. Now, from an application, an API point of view, you have a method you can call called setPreferredPHY, and you can request one of the 3 supported PHYs for independently for transmission and receive, and you'll get a call back to tell you what was agreed, because it depends what the remote device supports. Both must support LE2M if you're to be able to use LE2M, for example. The third PHY, by the way, I'm going to keep secret for the moment. We're going to come to it a bit later on. Last thing to be aware of where throughput's concerned and the various factors is this. The attribute protocol supports 2 different ways of writing data to a remote characteristic. either one or both, well actually either none of these will be supported, but for a characteristic that supports writing to its value, one or both of these can be supported, and that's a property of the characteristic itself. You don't have control over that in and of itself. If both are supported though, you can choose which one should be used. And the choice you'll be making will be based on whether reliability is most important to you or speed. Write requests are acknowledged. Every write request receives a write response from the remote device. That makes it a reliable protocol, reliable in the sense that you know that the application at the top of the stack received that data and confirmed that everything was good. But the write request response kind of sequence of events really slows things down. It's entirely serialized. Write commands, on the other hand, are fire and forget. You can write them as fast as you like. There are no requests to wait for, and it will be way faster than using write requests, but it's not reliable with respect to the application at the top of the stack, and that's worth understanding. Attribute protocol, obviously, it ultimately runs over the lower layers of the stack. The link layer in particular matters here. The link layer is acknowledging all packets that it receives. So at the bottom of the stack, there are acknowledgements running, and therefore, if your packet doesn't reach the remote device, you will know, and you'll get an error at the API level. However, what you won't know with write commands is if the packet reaches the remote device, did it find its way all the way to the top of the stack and into the application? What if there was a buffer overflow and the packet was discarded? You won't know that. So, you know, I have a heart rate monitor, which I don't really use very often, but I used to use it for cycling. In that instance, I really don't care if a few heart rate measurements are dropped. It doesn't matter at all. Equally, though, maybe a medical device in a hospital, it would be critical that all packets are received. So you have to make this choice between reliability and speed for throughput purposes. So, summary. These are the features, the variables that will govern the data rate that you can achieve. Larger MTU size is generally good, and you've got an API that lets you request it. You'll get a callback to on MTU change that will tell you what the outcome was. Data length extensions are either supported or not. They need to be supported in both devices for them to be available. It'll happen automatically. Nothing for you to worry about there. But if your project allows you to choose the devices that you're using, and sometimes that's the case in the enterprise, then choose ones that are just newer. Basically, newer devices tend to have the new features. Shorter connection intervals give more frequent opportunities for data to be transmitted, so you're probably going to get better throughput with a shorter interval, connection interval, so that's the high connection priority. Again, both devices kind of depends exactly what they support. And LE2M, the 2 megabit per second PHY, will probably give you an improved throughput, but not to the extent that you might hope. And you can see that you can check for supports from the local device that you're running on, and you can ask for a particular PHY, and you may or may not get what you ask for. So let me give you some numbers before we move on to the next topic, because this is quite dramatic, I think. I wrote an application a few weeks ago, and all it did was write 100K of fairly arbitrary data to a remote peripheral device over a connection. And I ran some tests with defaults, and I ran some tests with me using the APIs to optimize the throughput to the best of the device's abilities. And here's what happened. In the first case, I used write commands. So these are unreliable, but they're fast. Using the defaults, it took nearly 8 seconds to transfer 100K. But using my various tweaks and manipulation of variables, because I understand what they do, I managed to get that down to just over half a second. That's a dramatic improvement. And if you think about the user experience, half a second is a blink of an eye. No one's really going to notice. 8 seconds they'll know about. I then moved on to look at write requests and responses, which are slow but reliable. And as you can see, it took 500 seconds as opposed to 8 seconds with write commands to transfer 100K of the same data using the various defaults. But with my optimizations in place, that was reduced to 10 seconds, which is still slow compared to write commands, but dramatically faster compared to using the defaults. So data length extensions was used in all cases. The connection intervals you can see there on screen, I know those were the values agreed by the devices because I have a protocol analyzer and I was monitoring the connection setup procedure, so I could see what they agreed. But you can achieve an awful lot by a better understanding of the APIs and what they actually do under the hood. Let's move on to another subject, range. Range is a great topic because the majority of people, I still think, are of the view that Bluetooth has a range of 10 meters or 20 meters or something like that. And that's not the case anymore. The technology is 20 years old. It's been evolving the entire time, and many, many things have changed and improved. Range is not least amongst them. The first thing to understand before we get into this topic deeply, though, is what is it that constrains range in radio communications? Is it that the signal is no longer detectable by the receiver when we get to a certain distance? Well, the answer is actually no, the signal is still there. The problem is this. Take a moment to just absorb the slide that I have on screen right now. What I'm showing you is a blue line, which is the signal strength of a transmitted signal, and you're seeing it diminish as we get further away from the transmitter. Basically, there's some physics at work here. The energy is kind of dissipating as we get further and further away from the transmitter. So the signal strength measured at any particular distance is going to be lower and lower and lower. Now, the red line is important. The red line represents the level of noise, electromagnetic noise. It's always there in the background. It's caused by machines, devices, and natural sources as well. Now, the fact is, and again, this is largely about physics, there will be a point at which the signal strength gets sufficiently close to the level of the background noise that it starts to become difficult to decode the data that the signal contains. We're going to start to get errors, and errors can be detected by Bluetooth because every packet has a cyclic redundancy check field tacked onto the end of it. So Bluetooth, in all cases, can detect communication errors, and it may well hint to the sending device, hey, could you send that again? Because there was a problem. Definitely some of that data was corrupt, and corruption is occurring because our signal to noise ratio, that's the technical term, is getting lower and lower as we get further and further away from the transmitter. Now, being out of range is actually defined in more formal terms in our specification. We define a basic error rate, which is a percentage, and if it exceeds 0.1%, we basically deem the connection to no longer be working. At that point, we're out of range, the connection will drop, you'll get some kind of error at the API level and so on. So that's actually the nature of the range problem. It's about errors, their detection, and being able to correctly decode data in a signal when the signal to noise ratio is getting lower and lower and nearer to the background noise. So what can we do? We can increase the transmission power. In theory, a physicist might say that, but in the world of radio communications, there are regulatory bodies around the world that do not allow us to just increase the transmission power as high as we like. We have a ceiling, and assuming we're at that ceiling right now and seeing a certain range, what else can we do to increase range? Well, the answer concerns that third PHY that was released in Bluetooth 5. It's called the LE-coded PHY. LE-coded PHY uses a mathematical technique called forward error correction. And what this does is it adds additional bits sitting alongside every bit in your link layer packet that then gets transmitted over the air. Those additional bits get used at the receiver to drive an algorithm which is able to not only detect errors, but correct them up to a certain limit. What happens as a consequence of this is that even when we're getting further and further away from the transmitter and the signal to noise ratio is getting smaller and smaller and smaller, yes, we're getting more errors, but it's okay because forward error correction can fix them. So we can get further away, work at a signal to noise ratio which is much lower, and thus the range is increased. We say that the receiver is more sensitive. So if we just look at that graphically, This is where we started with no forward error corrections. The units are completely meaningless on this slide, by the way, but you can see at a certain distance from the transmitter, the signal strength has diminished. We're now at a point where the signal-to-noise ratio is giving rise to a certain level of errors. We're hitting our basic error rate limit. That's the limit of our range. And in terms of my completely arbitrary made-up units, we're at 6, or whatever that means, but you can see the principle. Whereas with forward error correction, it looks like this. We can work successfully keeping the basic error rate below the limit that's allowed, much, much further away from the transmitter. And you can see the signal to noise ratio is much lower here. The difference between our signal strength at the receiver and the noise level is very small now, but forward error correction can still fix things for us. And over 1 kilometre is possible today. Go to YouTube, you'll see people demonstrating this. And I have to tell you that whilst, if you like, the official figure that we tend to like to quote, and you can see people demonstrating it, is 1 kilometre, I met a Japanese manufacturer of consumer electronics last year at a conference, and they presented on this very topic, and in their testing they'd achieved 3 kilometres with Bluetooth Low Energy using the LE coded PHY, which is phenomenal. As Android developers, you have access to this if the 2 devices concerned support it. Okay, you can determine whether or not it's supported on the local device. You can request the use of LE coding through set preferred PHY. You can specify you want to use the LE coded PHY if your device is broadcasting, and so on. The one last thing to know is this: LE coded PHY can work in one of 2 ways, governed by a variable which has the incredibly imaginative name of S. That's right, we worked hard on that one. S can take a value of 2 or 8. You can see this at the bottom of my slide here. A value of 2 will double the amount of data that's transmitted. So for every bit in your link layer packet, there'll be another bit added for the purposes of forward error correction. So your 1000 megabits per second, which is the symbol rate, by the way, for LE coded, essentially becomes 500k bits per second. And you'll probably double the range approximately. If you use S equals 8, then the number of bits transmitted is multiplied by 8. For every data bit, every bit in your link layer packet, another 7 are added. So that reduces your bandwidth by an 8 to 125k bits per second, but you'll get the maximum range of about 4 times that which is normal, which is 250, 300 meters, something like that without LE coded. That's range. Let's talk about broadcast technology, or broadcast scenarios rather. So this is something that Bluetooth Low Energy can do, that Bluetooth BR, EDR cannot do. Let's start with some basics. So the procedure by which devices broadcast is technically called advertising. It's largely there, it was largely there in the beginning to facilitate device discovery, so you can connect to them. Bluetooth beacons leverage this capability as well. So an iBeacon will advertise or broadcast a unique ID, and your application receiving that broadcast message can look at the ID in a database and go, aha, the user is near to this particular place. That's an application of broadcast that's been quite popular. It's connectionless communication, so there's no connection setup step. There's no kind of coordination of timing. So devices wanting to receive broadcast data, advertising packets, are just going to have to scan for a relatively lengthy period of time, and you're going to miss some advertising packets and get some others. Advertising takes place on 3 specific radio channels. So Bluetooth works in the 2.4 gigahertz spectrum, but it divides that spectrum into 40 channels. Each channel is not a frequency, it's actually a frequency range. Oh, that was interesting. It's not a frequency, it's a frequency band. It's 2 megahertz wide, so there's a lower frequency and an upper frequency that define a particular channel. When we do that frequency shift keying stuff, we're using the central channel, the central frequency within the selected channel, and then we're shifting up or down by 85 kilohertz, staying within that channel, but encoding our 1s and 0s in that way. When you're in a connection, we hop across channels 0 to 36. That's called frequency hopping, and it makes connections very, very reliable in busy radio environments. But when we're advertising and doing connectionless communication, we're only using, by default, channels 37, 38, and 39, one at a time. That's how that works. So in busy environments where there's lots of devices advertising, this can start to be an area for some congestion to appear. Everyone's using those channels. Once again, in Bluetooth 5, a fantastic release of Bluetooth, something interesting happened. So instead of, I didn't tell you actually, the very small packets, 31 octets maximum that an advertising packet on those channels can accommodate, we now have things called advertising extensions, which are ancillary packets, which can hold up to 255 bytes. And the way they work is you will split your data across a primary advertising packet and the extension. There's essentially a pointer in the primary advertising packet, which still uses one of the three primary channels for advertising. And that pointer will point to the channel that the extension is going to be transmitted on. And as you can see, it's bigger, therefore we can pack more broadcast data into it in a single advertising extension. But it doesn't end there. We can chain advertising packets together. When I say we, the stack will do this for you. So there are pointers again between related segments of an advertising extension on different radio channels. So we're doing a kind of hopping now, but in a connectionless scenario, so it's more resilient. And the fact that we're using the entire 40 radio channels now is great spectral efficiency and means that we leave lots of capacity for devices to advertise. And of course, we get to broadcast at much larger payloads. Last but not least, there is the concept of the advertising set, because sometimes you want to advertise some data very infrequently, for example, but other data much more frequently. Eddystone beacons, for example, advertise some system data, telemetry information, and you probably want to advertise that quite infrequently, maybe once a minute, whereas the advertising packets that are there to guide location-based services, for example, you want to advertise more frequently. So advertising sets of data and associated parameters are formally separated, and you can set these up from Android and leverage them in the Bluetooth 5 stack. Gives you lots of flexibility. So, APIs. The good news is that when it comes to consuming extended advertising, chained or otherwise, the API and the stack do all the work for you. You don't need to do anything different. You're going to get scan record objects from the Bluetooth LE scanner scanning process. You'll call get bytes, and all of the related segments of your advertising packets will be joined up for you in a single byte array. So it's all done, which is cool. If you're using an application to advertise, you can determine if extended advertising is supported. You can create advertising sets. You can use extended advertising, which is tremendous. Last but not least, in terms of topics, I'm going to talk briefly about Bluetooth Mesh. I hope you're all still out there. If you're not familiar with Bluetooth Mesh, this is a completely new way of using Bluetooth to create whole networks of devices. Completely secure. Security is absolutely mandatory. Tens of thousands of devices can be part of your network, designed initially for smart buildings. In terms of stacks, Bluetooth Mesh is not the same as Bluetooth Low Energy. It uses the Bluetooth LE controller part of the stack that we have on screen now, but the host is completely different, has a bunch of layers that are specifically to do with mesh networking. You don't have that on your Android devices today. There are no native APIs for Bluetooth Mesh because Bluetooth Mesh is not supported natively by Android devices today. And why would you want to use Bluetooth Mesh from an Android application anyway? Well, consider a smart building full of lights and air conditioners and sensors. You do need applications with user interfaces for control, monitoring, and configuration of automation scenarios. So absolutely, you do need to be able to create web applications, mobile applications, and so on. So if you don't have a Bluetooth Mesh stack on your device, how can you do this? Well, the answer lies in the fact that Bluetooth Mesh defines a number of roles that devices that are part of the network can play. They're called nodes technically, and they can take on one of 4 special roles, including this one, which is called the proxy. The proxy is a node that has both variants of the Bluetooth low energy stack on it. It understands GAP, GATT, and the attribute protocol, the stuff that you have on your Android devices, but it also has the full mesh stack as well. So from an Android device, you can connect to a proxy. So you scan in the normal way, you discover proxies, you connect, and you can essentially wrap mesh PDUs, which are messages, and write them to the proxy by performing a standard characteristic write. You're injecting messages into the mesh network, and you can receive mesh messages in the opposite direction in the form of Bluetooth notifications. And I think this next slide shows that better. So a mesh proxy node, which is a device in the network, is not a special device. It could be a light, could be a light switch, could be a sensor, anything which has the right software on it to allow it to act as a proxy. It exposes a GATT service called the mesh proxy service. That has 2 characteristics in it, one called mesh proxy data in, one called mesh proxy data out. You can imagine what they're there for. So collectively, the proxy node has both protocol stacks like that. And your Android application, after connecting to the proxy, will perform GATT writes in the normal way, but formulating the value of the write such that it properly represents a mesh message, and receive GATT notifications, which are messages coming out of the mesh network that have been addressed to your device. And I'll tell you where you can find more information about all this stuff later on. I'm going to try and show you a quick video demo now. I'm going to stop my presentation and fire up this video. Just pause briefly. So what you have on screen right now is a kind of live screen recording of one of my Android devices with an application that I wrote I'm going to launch in a moment. The source code for this application is available from us, by the way. Again, I'll tell you where later on. Sitting next to it is a series of completely independent microcontroller-based devices that support Bluetooth, and I've programmed all of them to implement various aspects of Bluetooth mesh. So they're part of a mesh network. The entire 16 set of devices form a network. In the world of Bluetooth mesh, we work with things called models. These are granular kind of application layer behaviors or capabilities. The devices all have a colored LED, and I've implemented the models that let you switch them on or off by using mesh messages and let you change their color. Now, there's an addressing scheme used by Bluetooth mesh, which largely revolves around group addresses, and devices will subscribe to one or more group addresses, basically saying, I'm interested in receiving messages that are sent to these addresses. And devices which send messages, we say that they publish them, and they're usually published to a group address. So the entire set of 16 have all subscribed to an address that represents the whole grid. And I've also had each device subscribe to an address that represents the column it's in and the row that it's in. And I think all of that's also summarized here in the captions. So there's my 16 independent devices. I'm pulling one off the piece of cardboard I've attached it to, just so you can see what it looks like. That's a big battery in there, and there's a circuit board above it. Really nothing special, but they're certainly not connected in any other way than wirelessly. The models I've implemented in code are called generic on-off server model and the HSL server model. HSL is hue, saturation of light, it's color. Using my UI, I've connected to the proxy now. I've selected a particular address which represents all devices, and I've sent an on-off set message, and I've switched them all on. And now I've switched them off using the same address. I've changed the address to row 1, sent an on message. What am I doing next? I've chosen column 3, sent an on message, so those devices respond. I've switched back to the all messages, all devices address, switch them off, switch them back on. I'm now going to change that color. There you go. So I'm sending different types of Bluetooth mesh messages. They're all defined in the spec to specific addresses that each device has been configured to respond to. And I configure them through a configuration process when I set up my mesh network. So the summary here is that while you don't have mesh APIs on your devices, you do have the ability to work with mesh proxies and its protocol. So one of the variables you will have picked up here is that not all devices are the same. There are different versions of Bluetooth, and some of the features we've talked about are optional anyway. Bluetooth 5, for example, offers you 5 different PHY variants. Only one of them is mandatory. That's the LE1 and 1M, 5, 2M, and LE coded are optional. There's the sort of version history for you. Version 4 of the Bluetooth stack was the first time Bluetooth Low Energy appeared, and the ability to negotiate a larger MTU has always been there. At 4.2, the LE data packet length extension feature arrived. Version 5 delivered lots of good stuff, LE2M, LE coded, and LE advertising extensions. So again, if you're looking to decide what versions you wish to support for your application, this stuff is worth knowing. And be aware that the latest version of Bluetooth released is actually 5.2, which we released earlier this year. Handy application. This is called NRF Connect. It's in Google Play and it's free. It does loads of really useful things. This is the device information page. If you're curious about what your device can do, it will tell you, and it's using Android APIs to determine that information. What else might you see in the future? Close to wrapping up here, people, in case you're getting impatient. Well, 5.1 released last year delivered, amongst other things, a very accurate direction and ultimately location finding capability. 2 techniques, one called AOA, which stands for angle of arrival. The other stands for AOD, which is angle of departure. Either of those architectures involves either the receiver or the transmitter having an antenna array. And it uses something, a technique based on radio phase differences to very accurately determine the angle that a signal is being transmitted from. There are techniques which allow you to determine more than one angle from a single signal. And when you can do that, you can determine a location to within potentially 10 centimeters. Very accurate results are possible, designed for use in locations where there is no GPS, and 10 centimeters is way better than GPS anyway, but inside buildings, under the ground, this isn't in APIs yet, but this is going to be a bit of a game changer for location-based services. Last but not least, I think, LE audio. Bluetooth BR EDR, I mentioned right at the beginning, still probably a couple of billion of audio devices which use BR EDR are shipping every year. It's its major area of use these days. But earlier this year, we announced something called LE audio. LE audio replaces classic audio. Classic audio uses BR EDR. LE audio, per the name, uses Bluetooth Low Energy. But there's a lot more to it than that. It has a new codec called LC3. The codec gives you better quality audio, and it has a bunch of new facilities that are really cool. Classic audio allows you to wirelessly stream audio between 2 devices, because of course that's all Bluetooth BR EDR supports, point-to-point connections. LE audio is much more exciting than that. I'll start at the right-hand end. Audio sharing. Not only can I stream my music, let's say, direct to my headphones in a point-to-point connection, which I could always do with classic audio, but I can share audio either completely publicly or to a closed group. So maybe my Android phone is playing some tracks. I'm with a bunch of friends. They've all got Bluetooth LE audio headphones. They can listen to what I'm listening to, exactly synchronized as well, which I'll come on to. Multi-stream is amazing as well, because multi-stream means I can have different versions of my content streaming concurrently to that same group. Imagine you're sat on an aircraft and they're about to start the safety briefing. You've got your Bluetooth LE audio headphones on. You punch something into the panel in front of you in the seat, and you get to hear the safety briefing in Italian. The passenger next to me gets to hear it in English. Someone else gets to hear it in French. Very powerful capability. And the final one, lurking at position 3, is hearing aids. Believe it or not, there are no standards for wireless hearing aids today. So one of the primary use cases beyond consumer audio applications actually is the hearing aid industry, and this is going to be enormous. Sitting underneath, losing the ability to speak here, sitting underneath LE audio is a technical capability in the Bluetooth core stack called Isochronous Channels. And isochronous channels allow one device to communicate with multiple other devices in such a way that the processing of the data delivered is synchronized in time, very precisely. Look at the diagram there. I'm showing a couple of earbuds. They're independent devices, completely separate electronic devices, but they must process the audio data delivered to them at precisely the right time so that the user experience is as expected. And that's what Isochronous Channels gives you. And LE Audio is the first major application of Isochronous Channels. We anticipate more will come, and hopefully you'll see some of this in the world of Android at some point in the future. So where next? If you found any of this at all interesting, if any of you are still out there, it's very weird not being able to see you. Let me just point you at some things that you could go download and play with and read and kind of explore and fill in some gaps and take your learning to the next level. If you go to bluetooth.com/developer, you will find that we have a whole series of resources for developers called study guides. If in fact you go to bluetooth.com, I'm hoping you can see my screen now, and click on resources, and then click on study guides. Study guides, because these are self-paced educational resources for developers. Lots of hands-on stuff. It's not just dry theory. You get to code things, you get to make things. The LE Security Study Guide is there to teach you everything you ever wanted to know about security and Bluetooth Low Energy. Relevant to this talk, the Bluetooth Mesh Proxy function that tells you how to use the Proxy protocol so you can write Android applications, and the code for my demo is right in there. You can download it, look at the code. The Introduction to Bluetooth Low Energy Development covers all of the fundamental stuff. It's not necessarily simple, but it's all the fundamental stuff that you need to know, and it covers both the smartphone or client end of the architecture and the peripheral end as well. And if you're so inclined, you get to build a little bit of electronics and have a play. All good stuff. So that's, my friends, I believe, is a big thank you from me for your patience, assuming you're all still out there and I'm not talking to myself. Apologies again for the technical problems at the beginning, but computers are evil. You already know that. I believe we're going to have questions next, which I hope is going to work.
Thank you so much, Martin. This is Lucy James speaking from Droidcon Italy, from Synesthesia. Also from us, apologies for the delayed start, but Martin, thank you, brilliant recovery, excellent presentation. And yeah, I can confirm you've had an audience, and I'm quite sure there's a virtual applause happening right at this moment.
I can see the chat window now, so that's very reassuring. Thank you.
Definitely. I want to also say a thank you to Bluetooth, who have been the sponsor for this webinar. So thank you very much to them. There will now be Q&A. So all participants, you can write your questions in the messaging system, or you can ask using your microphone, but please use that sensibly. It might be easier to write them for management purposes. But back to you, Martin, for questions, and thank you again from us.
Okay.
So